Hello everyone, in this video we are going to talk about kinetics of a particle. So we talk about kinematics, which is motions of a body. Kinetics deals with the motion of the body in addition to the forces that causes that motion. So whenever we are dealing with forces, we are talking about kinetic forces that causes the motion. So basically it's a step up from kinematic. And then remember, we are talking about a particle, which means that the dimension is neglected. So no dimension. Therefore, we don't have any moment. We can use different coordinate system to solve our kinetics problem. Cartesian coordinate system, if our forces and acceleration are given in Cartesian coordinate, so Cartesian coordinate would be the easiest one to use. The summation of forces in x would be equal to mass times the acceleration in that direction. Summation of forces in y and z. The other coordinate that we deal with is normal and tangential coordinate system. So if the path is known, so the trick for normal and tangential coordinate, if the path is known, then it's best to use the normal and tangential coordinate system. And summation of forces in the normal direction would be m an, and an would be the velocity times the radius of curvature. So if the radius of curvature is constant, then this coordinate system would be very helpful. If it's changing, then we are better off with polar coordinate system. Tangential acceleration is just change of velocity over time. So this coordinate would be helpful if rho is constant. The other coordinate system is polar coordinate system, so it's more general. And we have, for this particle, if I want to write the coordinate, I have r and theta. Remember that theta is not tangent to the path because r is not perpendicular to the path, so it's very general. So we have summation of forces in the r will give us MAR. And if you remember, the radial component of acceleration would be r double dot minus r theta dot square. And summation of forces in theta is MA theta. Be r theta double dot plus 2r dot theta dot. So we named each of them. That was the slip part of acceleration when we have an acceleration in the direction of r. Here was the normal component. Here is tangential component. So this normal and tangential component are the same as the normal and tangential component in the previous coordinate system. So this coordinate system has additional acceleration if r is changing, because here we have r double dot that indicates that r is changing, and here r dot theta dot, that's Coriolis acceleration. And this polar coordinate system, if we are in 3D, in addition to r and theta, we can have z direction as well, which would be MAZ or MV double dot. But one thing that you need to pay attention is that for some problems we can use either polar coordinate system or tangential and normal. Let's say we have a particle moving along a circular path, and this is a circular, that means that r is the same, and then here we have theta. So if I use r and theta, I should get the same answer as if I use t and n. one thing that you would immediately notice is the direction of r and n. They are opposite direction, but then there is a negative in the equation that would take care of it. So here I have summation of forces MAR, summation of forces in theta, I will get MA theta. And here MAT, which is MV dot, and the other theta, and normal M AN M over R. So we are saying R here is constant, which means that R dot is 0 and R double dot is 0. So here in this equation, M R double dot would go 0, and I have MR theta dot squared. So that component would be present. Here R theta double dot would be present, but the Coriolis component would go to 0 because I don't have any R dot. So here my summation of forces in R will be reduced to negative M R theta dot. And summation of forces in theta would be reduced to MR theta double dot. And if I compare it with what I have for tangential and normal component, here n v squared over r. So what is the velocity? The velocity of this here would be r omega or r theta. So if I write r theta dot squared over r, you would see that the r in the denominator is cancelled with one of the r in the numerator. So at the end I have mr theta dot squared, which is very similar to this, but one of them is negative, the other one is positive, because our direction of n and r are in the opposite direction. Here same thing with tangential component, MAT. What is MAT? Is r alpha or r theta double dot. So if the radius is the same, you can use either polar coordinate or tangential and normal, and it would be the same. If the radius is changing, then we kind of don't know the path, so normal and tangential will not help us.